Hello, everyone. I'm Kristiina Jokinen from University of Helsinki and from CNRSI's Joint Research Lab in Japan. And I'm also a visiting professor at the Institute of Science, Tokyo. Today, I'm very happy to be here to talk about towards smart voice interfaces using grounding and knowledge, and I look forward to talking to you afterwards. Voice interfaces have come a long way since early voice XML about 20 years ago. From touchstone keys to automatic speech recognition, from pre-recorded audio files to text-to-speech outputs, and from form-based dialogues, which collect values for a set field of variables, to mixed initiative dialogue flows, we have currently, thanks to the surge of generative AI-based dialogue models, to reach near human-like conversations with a happy, friendly service agent as an expected interaction style, supporting chatting with the user. However, there are still challenges for smart voice interfaces that need to be addressed for the voice interfaces to gain wider acceptance as a smooth and enjoyable means to interact with digital services. An old joke says that we should educate users to speak to the system in the proper way so that the system can understand what it needs to do. Also, the amazing fluency of generative AI has introduced human-like conversations as a standard. The problem still is that systems basically understand the literal meaning of the user's utterance, not the user's intention, nor does it take the context into account. However, a paradigm shift is needed to understand the nature of spoken interactions. Language is dynamic, not a fixed set of literal meanings. Language is multimodal, socially embedded system that evolves through interaction, culture, and meaning making. In fact, this paradigm changes in how to define language is also supported by a recent article in Cognitive Science. In my research, we have tried to tackle the dynamic aspects of language in spoken interaction by the notion of grounding. It refers to means of constructing shared context through interaction to enable smoother, personalized, and more natural dialogues. The revolution in interaction research has not only concerned LLMs, but also knowledge graph technology and interface agent. Here is the workflow that we have used in building applications. We built knowledge graphs from existing reliable databases and texts. We stored the knowledge graphs in Neo4j graph databases, which are the industry standard. We developed GenAI interactions using retrieval augmented generation with LLMs and LangChain, and by using Neo4j's graph RAG framework. We also used LangGraph, an agentic architecture developed by LangChain. Important part is the Go design of the application together with the stakeholders to take into account different viewpoints, languages, knowledge levels, and preferences. This is to create a shared understanding on the design level. Finally, we wish to support the diversity in human and AI agent interaction, personalization, and multilinguality by adaptation to different dialogue styles, and ultimately enable learning through interaction and creating trust between the users and the AI agents. Based on our application experiences, we divided HRI errors into different categories. False implications are errors where the user is led to making assumptions that are untrue. For instance, the user is led to believe that the system has some information that it doesn't have. Ontological errors result from a lack of knowledge of the structure of the world, that is, not knowing that, for instance, Finnish food is a type of European food. Both of these types of errors can be remedied by using flexible searches and by adding metadata like taxonomies, geographical locations, and so on to the knowledge graphs. Theory of mind is a cognitive theory which proposes that the development of human cognition requires understanding of the other minds having different contents. The theory of mind errors refer to participants having different perspectives of the situation, disagreements which require clarification. The system thus must distinguish private knowledge and shared knowledge and have a mechanism for building shared information. I will not go deeper into speech recognition errors in this talk, which can actually make another talk. Please also see the papers and previous video for detailed examples and more discussion. So, what is grounding? We define grounding as a collaborative mechanism to establish shared knowledge in interaction. There are different types of grounding, which I introduce next. Conversational grounding deals with what has been talked about in the conversation and thus enables sensible dialogue flow. Grounding can take place on different levels, like making contact or perceiving that someone wants to speak. But usually we concern understanding of content of the utterance, the entities and propositions, including multimodal signals like nodding, which is commonly used as a feedback to signal understanding or non-understanding of what the partner said. Please see references for further information. Perceptual grounding is to ground utterances into perceptions of the world. That is, what kind of environment the speakers are in, what kind of entities are there, and how to refer to them. This helps to understand, to create a sense of the environment. It's the most common type of grounding in human-robot interactions, where the robot needs to operate in the real-world context. LLMs have brought a new type of grounding, namely grounding of information in the speaker's knowledge. That is, in the knowledge and experiences that the speakers have. This contributes to the level of reliability of the exchanged information. For instance, in our work, we can ground information into the carefully curated knowledge graphs to avoid LLM hallucinations and provide reliable knowledge to the user. In more chatty context, the system may need to apply filters to recognize bad language, unreliable and inappropriate context, even hate speech. To recognize that the knowledge of the users and AI systems is always partial and based on a particular viewpoint can actually help to resolve conflicts as well as reach satisfactory solutions in decision-making through interactions, argumentations, negotiations, and clarifications. Through the grounding process, it's possible to implement such interactive systems and explore solutions to avoid limitations inherent in reasoning and decision-making processes. Some references on the limits of knowledge can be found in the notions of minimal rationality and bounded rationality. As for the knowledge graph technology to build ground in dialogue systems, we propose to use knowledge graphs for different purposes in the whole system design. Domain graphs representing knowledge about the world, dialogue graphs about the dialogue, and document graphs about the human-curated documents which are embedded in the knowledge base. The grounding process proceeds incrementally as the dialogue progresses, and the grounding status of the semantic unit is attached as a property of the appropriate nodes. For instance, explicit grounding makes the grounding property to be added to the node's properties, while implicit grounding uses links that connect to the node to one which is explicitly grounded. The node is then treated as being grounded unless contrary evidence appears. The dialogue graph then is an interlinked graph where the nodes represent dialogue information on different levels. We have dialogues, turns, semantic units, and conversational entities. While dialogue standardization on the content level may be difficult, it's possible to try to build a standardized dialogue graph which can be used to model dialogue interaction and grounding. Unfortunately, I don't have enough time to go to details of the experiments that we have done on extracting grounded information and constructing grounded dialogue graphs to represent the dialogue. I will refer to our papers published in other forums. Another interesting topic for grounding is the memory and forgetting of the dialogue information. This has been studied in the context of cognitive architectures since 1980s, where an important aspect is the distinction between the short-term and working memory, or the working memory, and three types of long-term memories: semantic, episodic, and procedural memory. Recently, agentic architectures have brought cognitive issues into foreground, and we have also experimented with Koala, which is the new cognitive architecture designed to be used with modern generative AI language agents. LangGraph is designed to manage complex workflows with generative language agents, and it provides an implementation of many parts of Koala, including the memory structure. You can find more information in the references and also a dialogue example, which exemplifies how the constructed shared knowledge is still under control of the user, who can request the memory store to be deleted if she so wishes. The final point I wish to make is the personalization aspects for voice interaction, as the AI agents are not just one-time question-answer machines, but meant to be used in long-term interactions. Besides user preferences for voice, language, appearance, etc., which are customizable features, interactions also need to take into account the different expectations and background of the users. Different knowledge of the users, for instance, between doctors and patients or experts and novel users, need different type of responses that address their different level of expert knowledge. Sometimes the users can't precisely and concisely express what they are looking for, and they need suggestions and alternatives to elaborate what they are looking for. Interactions in different contexts differ, and the users also have different cultural backgrounds and expectations how the interaction can be managed. This is a takeaway summary of the aspects of smart voice interfaces that needs to be addressed to build usable, interactive, and language-capable applications. With the help of generative AI, a fluent natural dialogue between smart AI agents and users can be developed, but the system should also support grounding and long-term interactions with trustworthy AI agents. Personalization is an important aspect in this respect, and we continue exploring how to deal with it with the help of knowledge graphs and grounding. On a technical side, interoperability of the components to recognize and integrate many sources of information into a fully functioning system is important for seamless interaction and fast performance. Finally, I didn't talk very much about trust and security, but I'd like to finish by emphasizing the importance of the users being able to trust the AI agent operation and the inherent everyday biases in our communication, which require grounding and shared information construction to be solved. Naturally, control over the data to be shared and who has access to it is to be discussed and designed for practical applications. Thank you very much for listening. I'd also like to thank all the colleagues and project partners without whom the research could not have been progressed. If you wish to know more or contact me, please check the following pointers. Thank you.